Today we will learn about work and kinetic energy. In physics we say work is done only if an object is moved through some displacement while a force is applied to it. So we have our work equation where we have our force times our displacement will give us the amount of work done. And in order for work to be done, the force and the direction of the displacement have to be in the same direction. And we can express work in the unit of joules or Newton centimeter. We can see that force can be split into two components, one parallel and the other perpendicular to the direction of displacement. So we see that force is a vector quantity. However, only the component parallel to the direction of displacement does work on the object. So we see that our equation for work is force times cosine of theta times our displacement. When work is done on an object, the object put into motion. This motion is called kinetic energy. The kinetic energy of an object is its mass moving with a velocity. We see that kinetic energy can be defined as 1/2 times our mass times our velocity squared. We can see that kinetic energy, just like work, is expressed in the unit of joules. So we see here we have an example that states a student pushes on a heavy box with a force of 400 newtons and moves it a distance of 5 meters. If the force is applied at an angle of 37 degrees, find the work done by the student. If we state the information that we're given, we see we have a force of 400 newtons, a displacement of 5 meters, and an angle of 37 degrees below the horizontal. So we're asked to find the work done by the student. So we know work is defined as our force times our displacement. Since we have two components of force, the component of force we'll have to use is the component that is parallel to the direction of our linear displacement. We see that the force applied in the linear direction is summarized in our figure to the right, where we have force times cosine times our angle applied. So our force will be 400 newtons times our cosine of 37 degrees times our displacement of 5 meters. And when we multiply this out, we'll see that the total work done will be 1,600 joules. In our third example, we're asked to determine the kinetic energy of a Volkswagen that has a mass of 1,000 kilograms, moving at a velocity of 10 meters per second, and then find the kinetic energy of the Volkswagen if it's moving at 20 meters per second. So, if we find the kinetic energy of the Volkswagen when it's traveling at a velocity of 10 meters per second, we know that our formula for kinetic energy is equal to 1/2 our mass times our velocity squared. So we are given a mass of 1,000 kilograms and a velocity of 10 meters per second squared. We should get a kinetic energy equal to 50,000 joules of work done. And then part B, we're asked to find kinetic energy of the Beetle when it's moving at a velocity of 20 meters per second. So again, we will use the same equation, and we see that our mass hasn't changed, but our velocity has. Instead of being 10 meters per second, we have 20 meters per second squared. And if we multiply this through, we'll see the kinetic energy performed will be 200,000 joules of work.